You know, when we think about solar systems, we often picture ours, right? Fairly stable, planets doing their thing.
Yeah, relatively neat and tidy, you could say.
But space isn't always like that. It can be, well, pretty dynamic, sometimes even violent.
Oh, absolutely. There were systems out there that make ours look incredibly calm.
Like, take this binary star system, BD plus 054868. It's about 140 light years off.
Right, the one with the K dwarf and the M dwarf, so two suns already different.
Exactly. But the really wild part is this little rocky planet they found there, BD plus 054868 FI. It's in a bit of a sticky situation.
A very sticky situation. That's putting it mildly. What makes it fascinating is just how close it orbits the main star, the K dwarf.
How close are we talking?
So close that the heat and the gravity are, well, literally ripping into shreds. It's leaving behind these huge comet-like tails made of dust.
Wait, a rocky planet with comet tails made of dust. Okay, that sounds extreme. Let's dig into that.
Yeah.
So for this deep dive, our mission is basically to figure out how being that close causes it to just disintegrate.
Yeah, and what it must be like on the surface, how fast it's vanishing.
And why astronomers are so buzzed about watching this whole thing happen in real time. It's like catching a planet in its final act.
That's precisely it. It's a rare glimpse into planetary death. This all comes from work led by Mark Hahn at MIT, published in the Astrophysical Journal Letters.
And NASA's TESS spacecraft was key here. It spotted something weird.
Exactly. TESS looks for dips in starlight when planets pass in front of their star's transits. But the dips from this object weren't normal. They were messy, asymmetrical.
Messy how?
Instead of a sharp dip in recovery, the light stayed dimmer for longer after the main dip, suggesting something was trailing behind the planet. That turned out to be these huge dust tails.
Okay, so back to this incredibly close orbit. Give us some perspective compared to our system.
All right, think about Mercury, our innermost planet. This planet, BD plus 054868 AB, is about 20 times closer to its star than Mercury is to our sun.
20 times. Wow. That's practically skimming the star.
It basically is.
Yeah.
And that means its orbit is incredibly fast.
Right, its year must be super short.
Just 30.5 hours. A little over one Earth day to go all the way around.
Unbelievable. 30 and a half hours.
Yeah. And interestingly, while that's blisteringly fast, it's actually the longest orbital period we've seen for one of these disintegrating planets.
Huh. The others are even faster.
Yep. The others found so far are on even tighter, quicker orbits. This one's slightly slower pace, relatively speaking, might actually help us study the process orbit by orbit.
Okay, so it's close, it's hot. How does that heat lead to these dust tails you mentioned? Is it just boiling the rock away?
That's essentially it. The sheer heat from the star vaporizes the rock on the planet's surface, turns it straight into gas.
Wow.
Then, as that gas streams away from the planet, it cools down just enough to condense back into tiny solid particles like mineral dust.
And the star pushes this dust.
Exactly. The star's light, the radiation pressure, acts like a wind, pushing these dust grains away and shaping them into tails. One leads the planet, one trails behind.
Like a comet, but made of rock dust. And these tails, they're not small, right? I read the trailing one is enormous.
Gargantuan is the word. The trailing tail stretches up to 9 million kilometers.
9 million. How does that compare to its orbit size?
That's about half the length of its entire orbit. Imagine a trail of dust stretching halfway around its path.
That's incredible. Just visually, that's stunning. You called it catastrophic mass loss. Is it losing material faster than other similar planets?
It seems so, yeah.
Yeah.
The dips in starlight TESS saw were really deep, much deeper than for the other known disintegrating planets. That points to a lot more material being shed.
And you mentioned the dips weren't consistent. They changed.
Right. From one orbit to the next, the depth of the dip, how much light was blocked, actually varied.
What does that tell us?
It shows the whole process is really dynamic. The amount of dust in the tails is fluctuating. It's not a steady stream. It's messy, chaotic destruction.
So let's be clear about the tail's composition. Not ice and gas like a typical comet because it's too hot.
Precisely. Any ices or volatile gases would have been gone long ago or wouldn't condense that close to the star. What we're likely seeing are tiny grains of minerals, silicates, maybe iron, compounds, the actual stuff the planet's made of, boiling off and condensing.
It's like the planet shedding its own skin.
A very hot, rocky skin, yes.
And simulations help figure this out, how the tails form.
Yeah. Computer models were crucial. They simulated how dust particles of different sizes would behave under the star's radiation pressure.
And what did they show?
They showed that this pressure could create both a leading and a trailing tail. Grains feeling less pressure move a bit faster, forming the leading tail. Grains pushed more strongly lagged behind, forming that long trailing tail. The models also showed the trailing tail could vary in height or thickness, which helps explain why the starlight fades out gradually after the planet itself has passed by.
It paints a picture of just a hellscape. What do we think the surface is actually like?
Almost certainly a magma ocean, a world covered in molten lava. The estimated temperature is around 1,600 degrees Celsius. That's about 3,000 Fahrenheit.
3,000 degrees Fahrenheit. Hot enough to melt rock.
Absolutely, and that intense heat is what's driving the vaporization, boiling those minerals right off the surface into space.
Okay, we talked about the tails, but the actual rate of loss. How much material is vanishing?
The estimates are pretty mind-boggling. They calculate it's losing the equivalent mass of Mount Everest every single orbit.
Every 30.5 hours, an Everest worth of rock just gone.
Gone, poof, vaporized and blown away. Over the long term, that adds up to something like 10 Earth masses worth of material being lost every billion years.
That is catastrophic. At that rate, how long does the planet even have left?
Not long in cosmic terms. The estimates are maybe only 1 or 2 million years before it's completely gone.
A couple of million years. That's nothing, astronomically speaking.
It's a blink of an eye. And the process likely speeds up.
How so?
Well, as it loses mass, its gravity gets weaker. Weaker gravity means it's even easier for material to escape. So it's a runaway effect, a death spiral.
We're literally watching a world evaporate in real time. It's tragic for the planet, but you said it's a huge opportunity for science.
Exactly. It's incredibly rare to catch a planet in this final stage. Avish Borer, one of the researchers, said something like, "We got lucky. It's like on its last breath."
And the star being bright helps.
Hugely. BD plus 054868A is much brighter than the stars hosting the other few disintegrating planets we know. That makes follow-up studies much easier and more detailed.
And the big prize is using the James Webb Space Telescope, the JWST.
Yes. Observations are planned, I think, for summer 2025. The goal is to analyze the light filtering through those dust tails.
To figure out what the dust is made of.
Precisely. By getting the chemical fingerprint of the dust, we can work out the composition of the minerals evaporating from the planet. It's like a direct sample of its surface, or maybe even its mantle.
So the planet conveniently delivers samples of itself into space for us to analyze as it dies.
That's a great way to put it. It gives us a unique way to measure the bulk composition of a small, rocky exoplanet, which is usually incredibly difficult.
Why is knowing the composition so important? What does it tell us more broadly?
Understanding what these rocky worlds are made of helps us understand the diversity of planets out there, how they formed, their internal structure, maybe even their potential to host life, although obviously this one isn't habitable.
Right, not at 3,000 degrees.
No. But knowing its makeup informs our models of planet formation and evolution in general. Plus, the transits themselves are quite deep, often over 1% dimming, which makes them easier targets for these kinds of studies.
And it was kind of an accidental discovery. They weren't specifically looking for dying planets.
That's right. Mark Hahn was just looking through TESS data for regular planets and spotted this weird-looking signal. The asymmetry, the long tail after the main dip, that was the giveaway. A bit of luck involved.
And finding this one makes them want to look for more.
Oh, for sure. Now they know what kind of signal to look for. They're actively searching the TESS archives for more of these unusual asymmetrical transits. There might be others lurking in the data.
How many others did we know about before this one?
Only 3 others, I believe. And as I said, they orbited much fainter stars, making them harder to study in detail.
And do we know how long this has been going on? Is it a recent thing?
Well, they checked older ground-based data from a survey called ASASN, going back over a decade. It showed similar transit depths consistently over that time.
So it's been disintegrating like this for at least 10 years, probably much longer.
Seems that way, yes. This isn't a brand new event. We've just caught it in progress.
They also mentioned something about the 2 tails helping constrain the dust properties.
Right. The fact that there's both a leading and a trailing tail puts interesting limits on the physics, specifically the ratio between radiation pressure and gravity acting on the dust grains. They call it beta.
Okay.
Modeling that suggests the dust grains are relatively large, maybe around 1 to 10 micrometers. Smaller grains would get blown away too quickly or sublimate faster.
So tiny, but not super tiny dust. And does the amount of dust fit with the temperature?
Yes, the estimated mass loss rate, that Everest per orbit figure, seems consistent with how fast minerals like iron or silicates would vaporize at 1600 degrees Celsius. The physics hangs together.
Which reinforces that short lifespan estimate, the 1 or 2 million years.
Exactly. It all points towards a world rapidly approaching its end.
Okay, let's try to wrap this up. What are the absolute key takeaways about BD plus 054868, Abby?
Well, first, it's a rocky planet incredibly close to its star, getting baked. Second, this intense heat is vaporizing its surface, creating huge comet-like dust tails. Third, it's losing mass at an astonishing rate in Everest's every orbit, and likely only has a couple of million years left.
And fourth, it's a fantastic natural laboratory.
Absolutely. A rare chance to watch planetary destruction unfold, and crucially, to analyze the composition of a rocky exoplanet by studying its debris using telescopes like JWST.
So for anyone listening, even if you're new to this stuff, the takeaway is we're seeing a planet literally dissolve into space, and studying its death throes can teach us about how worlds live and die across the universe.
That sums it up perfectly. It's a dramatic reminder of the extreme environments out there and the insights we can gain by looking closely.
It really does make you wonder, doesn't it? What other completely bizarre planetary stories are playing out that we haven't even imagined yet? What else is waiting in the data? A fascinating, if slightly morbid, cosmic show. Thanks for diving into this one.
My pleasure. It's certainly a captivating system.